Recording is rolling. It is Tuesday, August 27th. So for context, today the first few classes, 10th graders were taking this past exam. So a few minutes of my class, they'll just have to catch this video. School announcement, Clash of the Clubs. So Ms. Barnhill is hosting this Clash of the Clubs. I did post this file to Google Classroom. So if you want to see this in detail, it's there. Coming up at, September 18, looks like. Okay. The auditorium, 6:30. If you're interested in participating in this, here's this application, which is due in a few days, August 30th. That's the end of this week, right? So you have to sign up pretty soon if you want to do this. This is a lip sync battle, but I meant to mention that. It's a lip sync battle. We got 1980s theme. Right, here's the application. Here's a list of rules. This is all posted in Google Classroom. How about clubs in general? What do I have on clubs? So there was an email sent out the other day that has a tentative list of clubs. So this is not complete yet. They said they have not officially released this yet. I think they're given more time for more clubs to start, right? But I went ahead and printed this out, and so you guys can see this. I did post this to Google Classroom also. Again, it's probably not complete yet. It'll probably change, or it might change the next couple weeks. But here's a bunch of clubs, and where to go for the clubs. Yeah. Okay, so you guys good on clubs? All right. All right, so let's get back to our story in physics, which is, you guys remember we've been doing linear motion. I was going through a PowerPoint yesterday and taking you guys through these posters one by one. So let me find about where we left off yesterday. I have to present this. Let me get back to right here. Here we go. All right. And so this is the slide I got to you yesterday that then the bell was ringing about. So I'm going to rewind a couple minutes, do a quick recap of these graphs, right? And then that'll give us momentum into rest of today. All right. So here I got the scenario of car drives at a constant velocity. Now that is actually even simpler than your guys' lab with the cars and the inclines. Because when you guys were rolling cars down inclines, were those cars going down at constant velocity or were they speeding up? Your Hot Wheels cars were speeding up, isn't that? Right? Which is not this scenario, right? This is even more basic. You just cruise control, just I-95 straight north, just constant velocity. You're not speeding up, you're not slowing down. Look at these graphs. I got displacement versus time, velocity versus time, acceleration versus time. And we've got units also. So variable unit, all the way down. Now that set of graphs, you're going to see all over the place in this class. So you're going to draw lots of axes for those graphs. Maybe have them in your notes from yesterday already. And all I'm going to do is change out the scenario. So I'll give you lots of different scenarios to say, hey, what do the graphs look like for this scenario or that scenario, right? So we're going to start real basic with our constant velocity. I usually start with the middle graph and then branch out from there. So constant velocity, that could be that. Look at that. It's velocity. That is constant, right? So you're not changing your velocity. You're not going faster or slower. So that could be that graph. That makes sense, right? The next one, how about displacement versus time? So you're definitely on the move. You're definitely acquiring location, right? But you're doing that at a constant rate. Hence x versus t is going to be a straight line for this scenario, right? And then how about acceleration versus time? What does that look like from yesterday? How much are you accelerating if you're at constant velocity? Yeah, 0. And so zoop, that's there's a 0 right there. They're right there, right? There are relationships among these graphs. So if you know one of these, if you have one of these established, you can kind of figure out what the other two look like, right? How about this? The rate change of your location. Guys, rate change of location, that's a really fancy way of saying what? Speed. Yeah, your rate change of location, that is speed. And on a graph, the rate change of something is the slope, like rise over run. See, like rise over run? Also, the units are consistent with that story. Like rise over run, could that be so many meters divided by so many seconds? Rise over run. Hey, meters per second. That describes the velocity, doesn't it? And notice how that slope is constant. You guys see the slope is constant, right? Therefore, the coordinate of velocity is also constant. Okay, so the slope of x versus t tells you the coordinate of v versus t. Do you think the same pattern applies from velocity to acceleration? Like the rate change of velocity, that's what acceleration is. Right? And guys, what's the slope of this v versus t? 0. Yeah, right. So same thing as the floor you're sitting on right now. Right? You can walk from one side of the room to the other side, and you're not changing your elevation. That's 0 slope. Therefore, the coordinate of acceleration versus time is also 0. You see how go from x to v and v to a, right? You can also go backwards. So How about from velocity to displacement? Like, guys, for example, if you go, let me use American units for a minute here. What if you go 60 miles an hour for 3 hours? Okay, 60 miles an hour for 3 hours. How far have you gone? 180 miles, right? Because all you do is multiply, right? Speed times time gives you distance, right? Of course, it's constant velocity, right? And on a graph, that would be represented by a shape. You guys see a green rectangle just popped up there, right? Ah, isn't the area of a rectangle base times height, right? That's what you guys just did. You said, okay, like the height of the rectangle could be 60 miles an hour, the base could be 3 hours, put it all together. Yeah, the area of that rectangle represents the distance you've gone. Ah, right. Again, it also works in terms of units. Miles per hour times hours, the hours goes away and you have miles. Right? All right, let's go back to metric. You guys want to go back to metric? Right? If I have velocity in meters per second and time in seconds, guys, what is meters per second multiplied by seconds? What is that? If you write meters over seconds and you multiply by seconds, and the seconds goes away, that leaves you with just meters, which again describes the distance. You see it? Okay, so the area under v versus t tells you the distance. Okay. Now there it's very simply a rectangle, right? But for other scenarios that are not constant velocity, it might be different shapes, maybe triangles or trapezoids, or you could have a crazy variable speed where you're like hitting the gas brake, and it's some crazy curve. The area under v versus t will still tell you how far the car has gone. Okay, as a general principle. Right? And then to tie everything together, that also works going from A up to V. And I'll show you guys how. Because what is the area between this acceleration curve and the time axis? What's the area? 0. There is no area, right? Because that curve is right on the axis. There's no area. What that means is that there's no change in velocity. I mean, that's what 0 acceleration is anyway, right? So whatever velocity you start with, it just doesn't change. Oh, look, that's exactly true, right? That's consistent with that. Right? That was a little bit more abstract, but that would be true. So it doesn't matter if you're going fast or slow, just whatever speed you happen to be going, you just can't change that. Okay. Right? You guys good? Right. And okay, so again, that's about where the bell was ringing yesterday. Right. So you guys ready for next page? Right, next one. All right. Ooh, guys, look at that question right there. Can you feel how fast a car is moving? That was a question that Paul Hewitt asked yesterday. You guys remember I played a bunch of Paul Hewitt videos yesterday? All right. Marissa, a similar question. Is the Earth spinning right now? It's going almost 1,000 miles per hour to the east we're going. Can you feel that? Can you feel that you're spinning? No. Right. You're flying in a plane at constant velocity. Can you feel how fast the plane is flying? No. If you're in a car going at constant velocity, can you feel how fast the car is going? No. You can feel something in a car, but it's not speed. It's what? Acceleration. Yeah. So like speeding up, slowing down. And a few weeks from now, we'll talk about the steering wheel. We're not quite ready for it. Right? So here, I've got some blanks here. Let's fill in some blanks here. So here's linear acceleration. It's just the rate change of velocity. That's to say, final velocity minus initial velocity. That could be a change of velocity. And then divided by the time interval. That's what delta t is, like a change in time, a time interval, right? So change of velocity per change in time could be your acceleration. That's the definition of acceleration. Okay. Of course, I got a blank beneath that, but I'm going to come back to that. Okay. You guys good so far? Right. We're going to toggle back and forth. So we'll come back to this PowerPoint, but I want to show you guys something here. So shuffle back and forth here. I just showed you guys acceleration is defined as change in velocity per time interval, right? Delta v over delta t. Okay. Write that out a little expanded form. So delta v, change in velocity. That could be final velocity minus initial velocity, all divided by, okay. I could do delta t for time interval. I'm going to do the same thing Paul Hewitt did yesterday, and I'm just going to write t, t for time. Okay, so I'm going to do that. I'm just a little bit. Okay, you guys good so far? So you guys saw. Let me do a little side story here. Sometimes you'll see this. Sometimes you'll see, what if you see little arrows written above the variables? That means something. I don't do this all the time, but sometimes I'll do this. Do you guys know what this means if the arrows are above the variables? It means it's a what kind of value? It means it's a vector value. Okay? And a vector means that direction matters. Right? So not only does it have a magnitude, like a number, but also direction. Okay? Notice I did not do that with time. Right? Time is considered to be a scalar. It doesn't really have a spatial direction. Right? But these other do. Right? Anyway, so let's keep going. What if I want to solve for this V final? Right, and I'm leading towards something, but we're going to do one algebra step at a time. Solve for this V final. Okay? Like how fast you picked up 2. Can you guys do the algebra and solve for that? So what's the next algebra step? Cross multiply the t. Okay, so acceleration times time. I'm going to drop those little vector arrows, but that's right. So cross multiply the t, get final velocity minus initial velocity. Got that. Okay. And okay, so I'm still trying to solve for this final velocity, the speed we're going to pick up to. Okay. Ooh, can I add over initial velocity? Okay. While I'm at it, I'm going to swap both sides and say this. Final velocity equals initial velocity plus acceleration times time. Okay. Okay. So let's see what we did this process. I started from the definition of acceleration. It's the rate change of your velocity. What rate are you speeding up or slowing down? Okay. And a few algebra steps later, I'm getting into this form. Okay, so the speed you pick up to is the speed you start with plus acceleration times time. Is that right? Right. All right. Now, that right there is going to be one of these 3 kinematic formulas. Specifically, this middle one. Isn't that exactly what we just derived starting from definition of acceleration? Just this one right here. Is that true? Right. Right. And let's tell you is you can be handed some number of linear motion puzzles, and there's this relationship between how fast something's going and how much time has passed, say in an accelerating situation. Right? You guys have kind of derived this before from another point of view. Back last week, you guys remember rolling the Hot Wheels cars down inclines, right? Some of you guys had stopwatches and speed gates. Hot Wheels cars would zip through the speed gates. How much time? What did that graph look like? V versus T. That's that one right there. Look at that. V versus T. Hey, look at that. It's a linear relationship. Ooh, also, guys, did you release the cars from rest or did you give the car a push? You released them from rest, right? Which means the initial velocity was what? 0, right? Because you didn't give it a push, you just released it. So 0. Oh, look, and it goes to the origin. Hey, you guys get it? So if this initial velocity was 0 because you released it from rest, now it just looks like the speed it picks up to is a times t. Ooh, and look at there. And now we can get a little bit more insight on this equation. We came up with this expression. We did a line of best fit, came up with an equation. Okay. Now you guys know that when I say speed is equal to 0.46 meters per second squared times t, this 0.46 meters per second squared represents the what of the car? Acceleration. That feeds in right there, doesn't it? Now you know how much the car was accelerating. Right? That's it. Right. But what if I ask a different question? Instead of saying how fast did the car pick up to, what if I want to know how far did the car roll? Ooh, could that be like x, like displacement? Right. So I want to drive all these with you guys, but so one at a time. So we got the middle one checked off, right? Right. Let's do this top one here. How far did the car roll x? Right. Now this one, I want to show you guys a few different perspectives. Some of it's going to have to be till tomorrow, right? So I got a PowerPoint slide, but it's going to be tomorrow, right? So I'll do a little bit today, and we did a little bit yesterday, and I'll show you guys. Okay? So let's start with this. What if you have a non-accelerating situation? Like the first slide you guys saw today, or last one yesterday, was the car drives at constant velocity. Guys, for a constant velocity scenario, what is acceleration equal to? 0, right? Ooh, would that mean this acceleration go away, right? Oh, look at that, look at that. Distance equals speed times time. You guys can do that, right? You've gone 60 miles an hour for 3 hours. You've gone 180 miles. Right? You guys do that? You guys do that? First, we're going to use meters and seconds. It's the same idea, right? Okay, so that's for 0 acceleration. Distance equals speed times time. You guys know that, right? What about this? Right, let's go back to your car in incline lab, which was accelerating. Now your car was accelerating, wasn't it? Right? In fact, you guys know how much. I bet it was about that much. Right? Right? So, but you guys did release the car from rest. If you release it from rest, what do you know about this initial velocity? 0. It zeroed out right there. Okay. So I'm making the claim x is 1/2 at squared. Okay. You might remember you did see this a little bit yesterday. You guys remember Paul? It was the second to last Paul Hewitt video I played for you guys. He derived this. Actually started from this, and then he was able to derive this. It took him a few steps on the chalkboard. Isn't that right? So if you want to go see that again, you can see an algebraic derivation of just this bit here. Now that's only starting from rest, right? It looks like that. Right. I want to show you guys the derivation of this graphically, but again, I'm not going to quite get to that in my PowerPoint today. So tomorrow I will show you guys the graphical derivation of this. Okay. Right. Now, let's put it all together. What if you back up. There's one more thing I want to say. That you guys actually have also seen this in a lab condition. Because some of you guys back with the car in the incline had a stopwatch and a meter stick. And you said, how far did the car roll in different time intervals? And on an X versus T graph, what shape did that make? Guys, how's this X related to this T? What shape does that make on a graph? Parabola. Yeah, all right. Guys do remember. And here it is right here. All right, X versus T. Hey, that was a parabola. Look at that. Right? Oh, and look at this. This 23 centimeters per second squared. Or maybe this was a different car on a slightly different incline. Right. But I'm making the claim here that number. Wait a minute. No. Oh, I just realized how these numbers worked out too good. I just realized this. Guys, I'm making the claim this 23 centimeters per second squared is this bit right here, half of acceleration. You see that? Right? Yeah, I'm just now noticing it for the first time today. Wow, I can't believe I missed this. Right, guys, look at this. If 23 centimeters per second squared is half the acceleration, then what is the full acceleration? Yeah, 46 centimeters per second squared, which is exactly what this graph on V versus T shows. Look at that. It's the same thing. You guys see that? It all connects. The opposite connects like that. Right? Right. Now, what if you gave the car a little push? If you give it a push, then all you have to do is add these two terms together. Just take my word for that now, and tomorrow I'll show you guys graphically that is true. Okay. If you give a car a push, you got the V naught. If it's accelerating, you got the A. Now you add the two terms together. Okay. You guys good? All right. Oh, okay. So that's got this one checked off. Got this one checked off. Right. Now notice that these are both in terms of time. How fast is the car going as a function of how much time, and how far is it rolled as a function of how much time. So check, right? What if I ask a different question? What if I say, what if I ask, how fast has the car picked up to, not as a function of time, right? But as a function of distance, like how far it's rolled. Ooh, how's the speed related to this X? That's a little bit different type question. Some of you guys had that version of the lab. And when you guys graph V versus X, what shape did that make? Was that like a square root type curve? Is that a square root type curve? Right? You guys remember that? Right. So maybe V is proportional to the square root of the rolling distance. Or if you square both sides, V squared is proportional to the rolling distance. See that? Right? Oh, and okay, that looks like this too. Right? Now you guys released the car from rest, so this initial velocity was 0. Oh, look at that. V squared is proportional to X. Right? Furthermore, I can say, I don't have an equation for that one, but if I did, there would be some number tagged to the X, and that would represent twice the acceleration. Right? Supposedly, I don't know. Is this third equation really true? Like, where does it come from? Oh, I can tell you. I'll tell you guys this. I'm not going to quite do this in class, at least not today, but if you do system of equations of the first two, if I take this time, because these first two have a lot of variables in common. So sometimes you're trying to solve some linear motion puzzle. And it's like, well, they have so much in common that is kind of limiting in a way, right? Like they both have the time ticking. They both involve acceleration possibly. And they both involve initial velocity possibly, right? So like on a Venn diagram, there'd be a lot of overlap, right? If you take this velocity versus time expression and solve for t, what would that look like? Vf minus v naught all divided by a, right? You substitute that into these t's up here. So vf minus v naught all divided by a here and here. And then you do a bunch of algebra, take like a whole page of paper. Guess what line you get at the end of that process? This third one right here. It can give you the velocity in terms of distance. Right? So you go. Right, so now we got these 3 kinematic expressions. And those 3 kinematic expressions can pretty well solve. Do you guys remember some time ago, did I give you guys a page looks like this? Right? This has 10 different linear motion scenarios. Linear motion could be backwards and forwards, maybe up and down, maybe throw a ball in the air, something like that. We won't quite get to this yet. I don't have a due date for this yet. I'll eventually pick this up from you guys, but not yet. But all the puzzles on this page, you can solve with these 3 expressions. Okay, that's it. So you could, I want to do some of them with you, and we'll do that sometime in the future. Okay? A little bit caveat to that, I should say. This very last scenario, you can actually solve a lot faster with a graph than the equations. All right, maybe hold on to that idea too. All right, so you guys good so far? You guys good? All right. All right, so let's flip back over to the PowerPoints. All right, so where are we in this thing? So I've got the definition of acceleration as the rate change of velocity. Turn that around, made one of those equations, and we're able to derive some other equations too. Okay. All right. Do you guys see this car going around a curve? Probably turn the steering wheel. Right. Now that's something you can also feel in a car. So that's a type of acceleration too. It's called centripetal acceleration. I'll give you guys the expression for it. That's the expression. We're not going to touch that for a few weeks. Okay. So don't worry about that one yet. So for the next few weeks, when I say acceleration, I'm really just talking about linear acceleration, like speeding up, slowing down. Okay. You guys good? You guys know this whole presentation you can download too. Did I tell you guys that too? I think first week materials on Google Classroom. I think under textbooks. I put this whole like everything for the whole year. Here we go. Okay. So here's your 3 kinematic expressions. Right. A lot of these made it to your thumbnail notes, but right. Well, I got a few extra, including this one. This one's a little bit extra. You guys see as I talk back and forth, one of these has the units written underneath, right? And then this one's like the clean version, right? Let's go to the one with the training wheels. Let's say with the units on it, because there's something that I want you guys to see, and this will be a general principle that's going to hold true for this entire class. And that's that you can only add like terms together, right? Let me start with a counter example, right? And then we'll go back to this, right? What if I ask you guys a crazy question like, somebody tell me this. What is 1 kilogram plus 3 seconds? What is that? 1 kilogram plus 3 seconds equals what? Is that a completely nonsensical question? How do you guys think? That question makes no sense. Yeah, that makes it. You can't answer that question. It doesn't have an answer, right? What is 3 miles plus 4 gallons? Does that make no sense? That makes no sense. Okay. Can I add gallons to gallons? Yeah, I can do that. Can I add seconds to seconds? Yeah, I can do that. Can you multiply and divide different units? I want so many meters divided by so many seconds. Yeah, you could do that, right? But you can only add or subtract the same units, right? So back to these expressions then, these kinematic formulas. Does that really hold true? Let's see if it does. Okay, so initial velocity, that could be in meters per second. Time could be in seconds. Guess what is meters per second multiplied by seconds? Meters. The seconds goes away, and now you just got meters. Is that true? Okay. Okay. How about this one over here? So I got 1/2 a/t squared. Acceleration could be in meters per second squared. Time could be in seconds, and don't forget it's being squared. So now you got square seconds from there. Put it all together. What does that give you? What is meters per second squared multiplied by square seconds? The seconds and seconds goes away. Now you get meters, just plain meters again, right? Because the square seconds and square seconds goes away. Now you just got meters. Right? Is that true? Okay. So this term is some number of meters. This term is some number of meters. Hey, I can add meters to meters, and that gives me meters, distance of meters. Look at that. Meters equals meters plus meters. Is that right? Guys, this is going to be true for this entire year. So like many weeks from now, when you guys learn in other kinds of variables and other kinds of units, don't do something like this. Don't say like, I'm going to add that force in newtons to this energy in joules, because that wouldn't make any sense, right? Got to make sure that you're adding like units together, right? Let's try the second equation here. Okay, final velocity, that could be in meters per second. Initial velocity, that could be meters per second. Okay, so we're good so far. What about acceleration times time? Say I got meters per second squared multiplied by seconds. What unit does that give you? Meters per second, because one of the seconds cancels and it just leaves you with meters per second. Plus this meters per second gives you meters per second. Okay. How about this last one? Final velocity squared. So that could be meters per second, but then you're squaring that whole term. So it's really meters squared per second squared. All right. Okay. This is also meters squared per second squared. So we're okay so far. Right. How about what is meters per second squared multiplied by meters? That's also meters squared per second squared, isn't it? And now I can add the terms together. You guys see that makes sense? Right. Then if I take the training wheels off, now we got these, right? I might recommend that you memorize these. I mean, I might not necessarily force you to memorize them, but maybe just after you guys solve so many physics puzzles, maybe just organically, you kind of know these after some time, right? But it could definitely be helpful, right, to really know these, because these are never going to go away, right? You're going to see these well, for the rest of the year. Sure. All right, what's we got? Yeah. Let me go back a bit. All right, so you guys know I handed you guys a whole page of linear motion puzzles the other day. We're working our way towards eventually getting to solve those. Okay. And if you want to solve any linear motion puzzle, you're going to have a question like you ask like how far did the car roll, for example, right? And I have to give you some information, like how far did the car roll? Well, maybe you have to know um, how much is it accelerating, if it is, right? Maybe you have to know it's something about speed. Maybe you have to know how much time has passed. Maybe you have to know, right? Okay. How about this? Let's zoom way back and let's get a forest for the trees view of what we're even juggling, what we're working with. Right? Guys, how many unique variables do you see on that page? How many unique variables? Like x could be a variable that shows up there and there. V naught initial velocity that shows up there and there and there. Okay, so now we got x, we got V naught, there's 2. Ooh, time, okay, that's it. There's 3. Right. How many unique variables do you see on that page? Do you guys see 5? You guys see 5? I think I see 5, right? Okay, so we got time, we got acceleration, we got x's displacement, and we got, 2 different velocities. We got initial velocity and final velocity. Of course, there could be a bajillion different velocities between, but all I care about is the beginning and the end of the interval. That's 5, right? Now, to solve any physics puzzle, any linear motion puzzle, I should say, okay, guess how many variables you have to be able to identify before you can solve it. Two's a good guess. Turns out that's not quite enough information. You need to be able to identify 3. Okay, right. Give you guys sort of an example here. I don't know if this is maybe kind of wacky example, or sometimes it is. I don't know. I always have to like cut activities or something, but I have so much time to work with, right? But sometimes it is. So I'll pull out some playing cards and just pop down some cards in front of these variables, and we'll make up a story. Say, what story could this represent? And therefore, can you solve for the 2 unknowns? Right. So I'll walk you guys through this one. Okay. So here's the 5 variables that we could be juggling with any of this. Right. Say I pop down cards like this. Okay. So time is 1 second. Acceleration can be 10 meters per second squared, and distance could be 5 meters. Right. What story can I make out of that? Well, you know what? Guys, acceleration is 10 meters per second squared. Hey, couldn't that be free fall gravity? Could be. Right? Let's attach it to that story. Let's say we go out to a cliff, and maybe I'm gonna either drop or throw a ball down towards the ground. Okay? And the cliff is 5 meters tall. So I've got a 5 meter tall cliff on Earth, hence acceleration is 10 meters per second squared free fall. Right? And let's say the ball reaches the ground after exactly 1 second. Okay. Now, once I give you that third piece of information, everything else snaps in place and becomes determinable. And that's to say, how fast did I throw the ball, or did I drop it? Maybe I did, right? And also, how fast is it crash landing? That's the final. Okay. All right. You guys see it? Right. And I'm going to go ahead and reveal the answers and work back from that and show you guys why this would be the case. Great. Right. So it turns out, and you can use those 3 kinematic formulas to verify this, right? That the only solution to that setup, 1 second, 10 meters per second squared, 5 meters, is that I had to drop the ball. You guys see initial velocity could be 0 meters per second. Okay, so starting from that answer, let's revisit that story again, forward in time. So I drop a ball off a cliff that's 5 meters tall on Earth, right? In that case, it will reach the ground in exactly 1 second, right? See, like if I threw the ball down, wouldn't it reach the ground faster, like less than a second? And if I threw the ball up and maybe it goes up and comes back down, then wouldn't it take more than a second, right? Okay, so the only way exactly a second on this cliff on Earth is I had to drop it, right? Furthermore, you can figure out how fast is crash landing. And if you run the equations, it turns out to be 10 meters per second in that case, okay? Right. Well, we'll do some numerical examples later today, but again, give you guys a like forest for the trees view of like the variables that we're juggling and how to make sense of this. Right? A lot of times you'll open up a physics textbook and okay, I see clearly I got a linear motion question. You can only identify 1 or 2 numbers that are explicitly printed. And sometimes those physics textbooks, they like to be a little bit sneaky. So guys, if you see something like drop a ball, like the word drop, guess what the word drop is telling you on these variables? It's telling you initial velocity, isn't it? Is 0 meters per second. What if you see this? A car brakes to a stop. Car brakes to a stop. I just told you a kinematic variable. Which kinematic variable did I just tell you? Final velocity is 0. Yeah, so you guys could kind of figure that out too, right? So sometimes you gotta dig around the words, like aha. Right. All right. So it's gonna bring us to this cliff. It's cliff time. So yeah, may or may not do this lab with you guys, but what you guys think, like in principle, could you do this? Right. Suppose you're we could do this out here. We could go out to the balcony and do this. Right? Or what if we're hopping around the galaxy? We're exploring different planets, like Star Trek or something. And let's say you go to, let's say you want to know what is the gravity field of that planet. Right? I wanted to figure out what's the gravity field of the planet. Again, we could do this here. We could go out to this balcony and we could say, how can I figure out what is the gravity field of maybe Earth or any other planet? So I go to the edge of a cliff. I'm going to drop a ball. And let's say you measure what is the height of the cliff. So maybe you could take a meter stick and measure like, see, 1, 2, 3, 4 meters, so many meters tall, right? And somebody brings a stopwatch. They see exactly how much time does it take for that ball to hit the ground, right? Now, are there 3 kinematic variables that are given in that scenario? Because if you drop the ball, do you know initial velocity? Yeah, because that would be 0 meters per second in that case. So we measure the height of the cliff, and somebody brought a stopwatch and said, how much time does it take? That's 3 kinematic variables, isn't it? Right? So therefore, do you think in principle, there's enough information that you could solve for the gravity field of the planet? Yeah, so you could do that, right? And like forest for the trees picture right here, just think, yeah, could do that, right? Right. All right, let's look at this cliff. So ball on the cliff, it's gonna be on Earth. We're gonna do this way. We're gonna switch over here, and you guys have your notes out, right? You guys got notes out? Okay. I'm gonna write a table. You guys draw the table along with me. Right here, I got the slide right here. Here we go. Right. So, you guys got rulers on your desk. I'm gonna pretty much copy this slide, but I'll do it with you guys so we can all pace ourselves the same. So scenario, drop ball off a cliff. Okay, so there you go. There's a scenario. Gonna drop the ball off a cliff, which by the way is just a sped up version of your cars rolling down your inclines, or vice versa. Your cars rolling down your inclines is really a slowed down version of this. Right? But it's gonna be same graph relationships if I graph this. Right? Right. Same type motion. There's some acceleration involved. Let's I'm gonna define down as the positive direction. Right. Which you don't have to do. You could call up positive or down positive. I'm going to call down positive. I'm going to call the top of the cliff 0.0. And as the ball is falling, it's falling into the positive direction, just so that all the numbers on my table are positive. Right. And let me throw on one more detail here. Right. Okay. So on the poster, I wrote that up here. Assume down is positive direction. I wrote another detail up here. I said assume no air drag. So I'm going to assume, use a little bit more technical term. I'm going to assume negligible air drag. Right. So in physics terms, negligible air drag could be either there's no air drag or you assume there's no air drag, or if there is air drag, it's so small, it's so insignificant that it's not really going to mess up your math. Okay. So, yeah. So for the next couple of weeks, we're going to assume there's no air drag. Okay. All right. And I got a table. And the table is 1, 2, 3, 4 columns and 1, 2, 3, 4, 5, 6, 7 rows, right? Including the title row, right? So let's do that. Let's whip off a table here. Okay. I got 1, 2. Here's my 4 columns and zip. 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 All right, a bunch of rows. Oh, you know what might be a good idea too is maybe draw this little picture here. You guys see I got a picture of the cliff, right? I'm gonna drop a ball off the edge. It's gonna fall. Right? Oh, and look how the ball is like spreading out. Like if I take a picture every second. So right when I release the ball, I take a picture. I take a picture 1 second later. And then 1 second later. 1 second later. 1 second later. 1 second later. You see how every successive second it's like moving a further distance than the previous second? Probably makes sense because it's going faster, faster, faster. It's picking up speed. I bet if you graphed distance fallen versus time, it would be a parabola type shape. It's like spreading out. Is that? All right. Let's do, oh, I gotta put some spills up. I got time in seconds. I'm gonna get acceleration in meters per second squared. We're gonna do velocity in meters per second. We're gonna do distance fallen, or displacement if you like, in meters from the edge of the cliff. Boom, 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 boom. Just like that. So there you go. Just copy down that table. So make sure you guys are caught up to where I am. I think you guys are. All right. Ready to good? We're going to say what's happening 1 second at a time. So here, I'll give you guys a time column. So go from time zero. So time zero, I just dropped the ball. And then we're saying what's happening every second. So after 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, and maybe at 5 seconds, it's just about to hit the ground. You guys see it's like a millimeter above the ground. Okay, so okay. All right. So you guys got in your notes, looks about like that. And from here on out, I'm gonna just refer to this table. Sorry, cover something. All right, here we go. All right, everybody, all right? All right, so I'm at the edge of a cliff. I'm gonna drop this ball. Okay. Now I know it says time 0 seconds. Let's call it maybe like 0.001 seconds, like a millisecond. That could be right, millisecond. So I've released the ball like a millisecond ago. So is it under the influence of Earth's gravity? Yeah. So Earth's gravity field is starting to pull it down. Right? At what rate? Because what is Earth's gravity field right after I release it? What number goes in this cell right here? 10 meters per second squared. There you go, 10 meters per second squared. Okay. I think earlier today, or maybe you guys yesterday, told me more precisely it's like 9.8, but more often than not, I'll tend to round it to 10. Okay. If you see 9.8 on any materials, like, okay, we're still on Earth. Okay. Let's call it 10 meters per second squared. Okay. Now, suppose it's been falling for 1 second. Okay. Is Earth's gravity field still pulling down at 10 meters per second squared? I see you guys nodding. You guys are saying yes. You guys are saying, yep, after 1 second, still pulling at 10 meters per second squared. It's the same gravity field. Huh. How about after 2 seconds? Now it's accelerating how much? 10 meters per second squared. That's right. That's right. How about after 3 seconds? How much is it accelerating? Is it still 10 meters per second squared? Yeah, sure is. Right. Is that true all the way down? All the way until it hits the ground? Sure is. Sure is. It's 10 meters per second squared all the way down. Yeah, that'll be pretty well a constant value right there. Now, of course, after it hits the ground, now goes to 0 and it stops. But the entire time it's in free fall. Okay? That's why I'm saying after 5 seconds, maybe it's still a millimeter above the ground because it's got the slam to it. It hasn't quite hit the ground yet. All right? Okay, you guys good? All right, you guys ready for the velocity column? Okay. All right. Now, what number do you think goes in this cell right here? Who has a good guess? 0. Exactly. Exactly. Right. Here's why. Or maybe I should ask you, right? Guys, what in the scenario setup told you that number has to be 0 meters per second? That word right there, drop. Yeah. When you open up the physics textbook, you see the word drop. Oh, you know, initial velocity, 0 meters per second. Because we're not throwing the ball. If you threw it, then that would be some non-zero number. Okay? So drop, drop, 0, hand in hand. Right? Guys good? All right. How about after 1 second, it's picked up to how fast? Huh? Well, I know it's picking up 10 meters per second per second. 1 second has passed. That means it's moving how fast? 10 meters per second. Yeah, 10 meters per second. If you want an equation for this, because some of you guys might want an equation, could that be this one right here? How fast is it going as a function of time? That's this one, isn't it? Okay, so I dropped the ball. Let's release it from S. This one goes away. Right. Here, maybe I'll write this out on paper. Should write some of this on paper, right? So I'm going to write out final velocity equals initial velocity plus acceleration times time. Right? Now, initial velocity was 0 meters per second, so that goes away. I'm going to modify this a little bit. Can I say acceleration is specifically Earth gravity? Do something like that? You can do that, right? So that is that. And then now let's get some numbers. So I need 10 meters per second squared. It's right there. Okay. Let's do it for 1 second. So 1 of the seconds goes away. It gives me 10 meters per second. Okay. How about after? Let's do it. Let's do a new question. How about after 2 seconds? 10 meters per second squared. It's accelerating. Does that for 2 seconds. Now how fast is it going? 20 meters per second. New question. How about it's still a free fall, 10 meters per second squared. It's doing that for 3 seconds. Now how fast is it going? 30 meters per second, right? Oh, and then the units also work too, right? Meters per second squared times seconds gives you meters per second. Okay, is that true? Okay. You guys see a pattern, but you guys see the pattern. Okay. So after 1 second, it's picked up to 10 meters per second. After 2 seconds, ooh, now it's twice as fast. After 3 seconds, ooh, now it's up to 30 meters per second. Right? How about after 4 seconds? How fast? Yeah, 40 meters per second. And then how about 5 seconds? It's just about to slam into the ground at how fast? 50 meters per second. So you guys got that column? Okay. And remember, that was also like if you graph v versus t, what shape would that make? Same as you got with your car and incline lab, right? Okay. So now for pure free fall, 1 second goes up to 10 meters per second, then 220, 330, 440. Still makes a linear relationship, right? All right. Now, how about this next one? How far has the ball fallen? Okay, so each second. How far has the ball fallen? Now, this one's a little trickier. This one's a little trickier. I do need to give you guys a number. I need to give you guys this number. Okay. I'm going to define the top of the cliff as 0.0. Okay, so go ahead and just write that one in. Okay. So the top of the cliff, I'm just going to call 0.0. Okay. And now I'm going to say how far has the ball fallen from that point. So here's a little bit tricky question. A lot of students missed this next question I'm about to ask. I wonder if you guys are going to get this. How far does the ball fall in 1 second? Starting from rest. How far does the ball fall? 1 second. And if you don't know, then maybe I bet this could help, right? Ooh, here's how far as a function of how much time could that be, right there, right? Let's do the math. Let's do the math on this. Right, so math time. Okay. So that first kinematic formula, I'm going to say here's the full version. X equals v naught t plus half at squared. Right? But I can simplify this. So I know if I drop it, then v naught 0 goes away, 0, whatever. It goes away, 0. I might do this just to get you guys used to different looking variables. I'm going to say a height change. Can the height change be x could be a general displacement? I'm going to use h for height, like a height change. Okay. And then I got 1/2. Instead of a, I'll call it g, and then t could still be t. That's okay. So, 1/2 gt squared. Okay. Let's plug in some times. So height changes. So we got 1/2. Let's go 10 meters per second squared. Let's let it go for 1 second. 1 second. And don't forget to square the time, although 1 squared is still 1. If you didn't see it before, I bet you see it now. How far is that? 5 meters. 5 meters. If you go to the edge of any cliff on Earth and drop a ball, after 1 second, it's going to fall 5 meters. Right? And then the units also work because second squared and second squared cancel. Meters is meters. Okay. So now we got one number on the board. We got point that right there. So you guys got that one? How about after 2 seconds? How far total has it fallen after 2 seconds? 20 meters, exactly. Here, I'll do the math. Right, 20 meters. You guys got it. You guys are ahead of me. Okay, so 10 meters per second squared. We're doing 2 seconds. Square the time. 2 squared is 4 times 5 is 20. And the unit seconds squared and seconds squared is meters. Yeah, 20 meters. 20 meters. Okay. How about after 3 seconds? Let's try that. So 10 meters per second squared. We're doing 3 seconds. Now square the time. Guess what's 3 squared? 9 times 5 is 45. 45 meters. Aha. Right. Now, this is all relative to the edge of the cliff. So cliff is 0.0. After 1 second, it fell a total of 5 meters. After 2 seconds, it fell a total of 20 meters. And 3 seconds, a total of 45 meters. Right. Let's finish off this table. How about after 4 seconds? How far total did it fall? 80 meters. Right. Right. How about after 5 seconds? How far did it fall? About 125 meters. That's right. In fact, I think you guys saw that one yesterday. Do you guys remember the Paul Hewitt story? You walk into a 2K. There's an old mine shaft. Can't see the bottom. Hear the bats. I wonder how deep it goes. Give me that rock. Drop the rock. 1, 2, 3, 4. It takes 5 seconds for the rock to hit the bottom. Right. So how deep is it? It's about 125 meters deep. How'd you know that? College. And here's the college equation right here. I drop the rock, so this bit goes away. Because remember, I had the height change is 1/2 gt squared. Ah, that's not right there. That's the college equation, isn't it? That sure is. That's it. All right. So you guys good on that cliff? That's good. All right. Let's see where I am here. All right, so back over to PowerPoint. All right, so scenarios: drop off a cliff. There's the table of values. We've got a whole big table. Could you get lots of graphs out of this? Could you guys graph, see X versus T and B versus T and A versus T, make at least 3 graphs out of that, right? That's the next slide. Look at that. It's the exact same scenario, but instead of a table, I have the graphs. But it's all the same information, isn't it? Right? And just like the car that was driving that we looked at end of yesterday and beginning of today, these graphs are related to each other. And I wrote in how they related to each other. So this is the first thing I'm going to do tomorrow. I'm going to wrap up today and then see this end of today and beginning of tomorrow. Right? If you take the rate change of position, that gives you the velocity. Now, this one is more complicated than the car at constant velocity because this is an accelerating situation. Guys, rate change, that's the slope of a graph. Right? Can you hold your ruler or your pen like flush to the curve? But then different points of the curve, look, the slope is always different. I put V1, V2, V3, V4, V5, right? Because the rate change of position as a function of time, right? Yeah, that slope is always changing. And the slope, of course, is velocity. That's all different velocities. Now, if you plot those velocities at each successive second, they're all going to line up in a straight line. Zip, you're a line best fit. It's a linear relationship, right? And since that has a constant slope, hey, that rate, guys, what's the rate change of velocity called? What's the physics term for that? Rate change of velocity. That's called, starts with an A, acceleration. Hey, so that constant slope on V versus T is the constant coordinate on A versus T, which is, in this case, free fall gravity, isn't it? Ah, right. And then you can go the other way around because that's all these red arrows going down, down, down the line, right? But you can go the other way too. So acceleration times time. Guys, what does acceleration times time equal to? Like a change in velocity. Hey, that's this green arrow up here. Right? And how about velocity times time? That tells you like displacement, right? Now here we have a change in velocity, so it's a little tricky, but it'd be this triangle. After you do that beginning of class tomorrow, I want to show you guys. I'm going to derive 1/2 AT squared graphically from this graph, basically, right? That brings you back to this X versus T parabola type shape, right? You know what? One more detail I'll throw at you guys here. The math that I was just talking about that links those 3 graphs together. Does anybody know what math you guys were just doing? Who's taking calculus? Who's taking calculus? That's calculus. That's what calculus is. Calculus is, well, the first half is rates of change. And the second half is called integration, which is just the same process backwards. That's it. That's a calculus slide right there. All right, that's a good pause point today, and we'll pick up the story tomorrow. And of course, we're working towards those linear motion puzzles. So in time, we're getting there, one day at a time. All right, be good day.